So hello, everyone. Thank you very much for joining this session. My name is Lapczyck. I am security engineer at Queen's University's Center for Advanced Computing. And today's session will be about analyzing the encrypted traffic, more specifically, Microsoft Remote Desktop Protocol. And I will tell you about some security and privacy issues, unfortunately existing in that RDP Remote Desktop Protocol traffic. So what is this presentation about? So it is about our study that we conducted on RDP protocol traffic, where we're investigating 5 main activities inside of encrypted traffic without the need to decrypt the traffic. The main motivation behind this study was my work experience in secure environments, and Remote Desktop Protocol is one of those protocols which is very widely adopted. So you can find it in pretty much any kind of public or private sector organization on any kinds of networks, ranging from small to big, from very simple to very complex. And unfortunately, analyzing encrypted traffic is not always an easy task, because normally that would require traffic decryption between 2 endpoints, which is not always possible, or at least not always feasible. So encrypted traffic nowadays is growing. It's available pretty much everywhere. The role of the cybersecurity is often called to protect the CIA triad. And this is the confidentiality, integrity, and availability of systems, networks, communications, data, whatever. There is an increasing use and reliance on encryption. And for that reason, users often assume that encryption guarantees security and privacy of their communications, which unfortunately is true only to a certain extent, as I will explain in a few minutes. So in our study, we investigated 5 main activities carried over encrypted RDP sessions. And this is downloading a file, browsing the web, typing in a notepad, watching a movie, and copying and pasting contents via the clipboard. So what is the Remote Desktop Protocol? Just a very short intro. That's a Microsoft protocol built into Windows operating systems. And as you can see on the diagram over here, there is an RDP client connecting to RDP server. So the client can talk via Remote Desktop Protocol to the server. The user can perform tasks on the server by using local keyboard, local mouse, local speakers, local screen. The user can as well use clipboard, mount drives to exchange files back and forth. The traffic is encrypted in transit with TLS, Transport Layer Security Protocol. And it uses TCP and UDP transport protocols whenever possible. Some environments only allow TCP, which I'll also describe in a minute. For our study, we collected 18 hours of Remote Desktop Protocol traffic, which translates into 2,160 30-second Remote Desktop Protocol traffic samples. And those samples included pure samples where there was only one activity in each sample. So for example, there was only a file download, or the user was just typing some text in text editor. But there were also mixed samples. So the user could be watching a video, downloading a file, and typing at the same time. And with mixed samples, we went up to 4 simultaneous behaviors, 4 simultaneous activities. And we collected data for local traffic. That would be portrayed by the diagram on the right. If you take a look at workstation 01, this is always our Remote Desktop client, and it's connecting to Win01 virtual machine, which is on the local subnet. So that was the local traffic, and transport protocols were TCP and UDP, because that is enabled by default. We also collected traffic to the remote virtual machine. So workstation 01 had to escape our subnet, traverse the internet, connect to Queen's University's Center for Advanced Computing firewall, which would allow it to connect to CEC01 virtual machine. And that communication happened only over TCP transport protocol, which is the case in many firewalled environments. One of the key points of any data analytics studies is feature extraction. We need to be able to extract some statistical features about the data we're going to analyze. So in network communications, the basic communication message is called a packet. And a single packet sent from client to server or the other way around has three basic properties. And that would be direction, that would be size, and that would be time. These three are absolutely unaffected by encryption. So even if the traffic is encryption, we can tell the direction, which can be forward or backward. Forward is client sending something to the server. Backward is the server responding to the client. We can measure the size of a packet being transmitted, and we can tell exact time of when a packet was sent. From those features, we can build larger data sets. We can calculate their averages, standard deviation, minimum, maximum. We can count specific packets that we find interesting or important for a particular study. And we extracted over 100 statistical features after calculating those derived features and using some matrix transformation techniques. So over 100 statistical features on every sample of encrypted traffic. Data exploration was vital because that allowed us to discover some extremely important features. And let me share some of the interesting findings. Some packets length discloses what the user is doing precisely. 92-byte frames or packets for simplicity, two of those are sent forward, so from the client to the server, whenever a user presses a single key on their machine. 97-byte packets are sent whenever the user uses their mouse to do any kind of scrolling, clicks, mouse movements. So that tells us something about the user's activities involving mouse. 104-byte frames are sent for mouse movements alone. So only by looking at the stream of 92, 97, and 104-byte packets, we can safely determine what the user is doing when the user is typing and that kind of stuff. Another important thing, the length of the returning packets. As we can see on the diagram on the right, well, the length of the returning packets could suggest number of pixels needed to update on a screen. So that's the visual output. So a user presses a key, and let's follow the diagram on the right. The single keystroke is sent from the client to a server using this one 92-byte frame. The server responds following TCP/IP communication standards with acknowledgement as first frame acknowledgement. The client sends the second 92-byte frame. The server responds with another acknowledgement, but it also sends a super interesting packet with a push flag. Push flag is added to push data to client. And in this case, it is data that's likely related to visual output on the user's screen. So the longer packet is sent, the more likely a user is sending characters such as 8, G, or K. For hyphen or period, those packets would be shorter. So it might be tricky to determine exactly what character is sent, but what group of character the user is typing, that could be something potentially doable. Next, our classification task. In the table on the right shows accuracies with standard deviation across cross-validation. It shows accuracies for specific behaviors, and the upper part of the table is for the remote virtual machine traffic. The lower part of the table, the lower half, is for the local subnet virtual machine. So as you can see, we achieved scores in high 90s, so we've done pretty well. We used 7 techniques on samples belonging to one or more of the behavioral classes. So every sample was evaluated using 7 of the techniques, leading edge classification techniques used in data analytics. And the 3 best performing techniques for each of the data sets, please keep in mind, the upper half is remote, the lower half of the table is the local subnet virtual machine. 3 best performing techniques for each of the behaviors, for example, for download, were selected to build a stronger predictor. And we did that to minimize the number of false positives. False positives are minimized when we combine predictors And as you can see in this table, in the highlighted area, there are very few false positives. They are rare. And that's because we implemented voting. So out of those 3 predictors we chose for each of the behavioral classes, at least 2 had to agree on a positive occurrence before calling a sample positive. So we either needed 2 or 3 yes votes to decide that a sample is positive. If there's only one of the techniques claiming that a sample is positive, we don't trust it. It's likely a false positive. Scoring function that penalizes false positives was employed. So for every true positive, the scoring function gave us +1. For every false positive, it removed 2 points. And for every true negative or false negative, there was 0 points added. So +1 for true positive, -2 for false positive, 0s for false negative or true negative. And the reason is we wanted a function that will evaluate how well we're doing at avoiding the false positives. So we developed this ensemble score. The maximum score that can be achieved is 100. And for both the TCP or the remote machine traffic and the UDP, which is the local subnet virtual machine traffic, we achieved scores higher than 97 of average over 5-fold cross-validation. So again, we've done very well. Some traffic classes reach 100% accuracy, which is absolutely amazing because that means that there are 0 false positives and 0 false negatives. So classification is 100% accurate for those behavioral classes. Some conclusions which are worth sharing. Some behaviors might dominate others, which means if there are 2 concurrent activities, one might make it difficult to predict the other one. And there are 2 examples, download traffic dominating YouTube. That's because both of them focus on the server sending lots of data back to the client. However, download is usually a bit bulkier traffic, uses longer packets. YouTube only needs to transmit video output and audio stream. Browsing and clipboard may be confused. And that's because both of these behaviors involve mouse movements, mouse clicks, selecting some area, right-clicking, copy, and that kind of stuff. However, please note that we don't get too many misclassifications, but they still do occur. And why it's important is some activities may be masqueraded by a user. So a user who's watching some videos, who's slacking, who's not working, might start some download session in the background as well to trick our system and to try to trick our system and to pretend that he's actually not watching, he's downloading something. So either way, it's important because attackers might try to masquerade their behaviors. They might conceal one behavior and another noisier behavior. We worked on 30-second traffic samples, which is a reasonable approach because that's way faster to process than real-time packet streams, which makes our predictor a good candidate for, which makes our approach a good candidate for production systems. Whether a user is watching YouTube or watching an MP4 movie, we can still predict the overall activity. So again, the slacking user is watching some kind of a movie, and even if he changes the application from watching YouTube on the web to using whatever local application for MP4 movies, we can still detect the overall activity. So let's summarize what we found, the security and privacy implications. We can predict 5 general behaviors. As I said, download, browsing, typing, watching a movie, copying from a clipboard. We can tell users granular actions, so mouse movements, mouse clicks, scrolling, typing on a keyboard, and we can go as far as tell when user is moving their mouse, how intensely, how many clicks or scrolls are performed, how many characters the user has typed on their keyboard, and when a key is held. That has very particular markers because there are equally spaced subsequent packets, 92-byte packets. So it is very visible in the network logs. So that leads us to a conclusion that it's possible to predict the length of typed passwords. So even if though the connection is encrypted, we can still count those 92-byte frames, see when a user is pressing the buttons, how many keystrokes are sent, and we can predict the length of the passwords that were typed. Again, packets responsible for the visual output could suggest what the user is typing. It may not work for the passwords, since there's usually a filler for every character the user is typing on the screen. So there's either a dot or some other filler character displayed. But for whatever the user is typing on the screen, there might be something that attacker could potentially detect. Using all of the above, all of these things I just discussed, as building blocks, we can build a behavioral profile of users. And that could be extremely useful for building anomaly detection systems where behavioral patterns are described. And when we see some kind of an anomaly, we might decide that this is not the regular user that is normally using this account. We can learn something about the traffic by looking at the protocol alone, which is very simple. So when we see TCP and UDP stream, we know that it might be local, it is likely a local subnet traffic, or there is some more relaxed firewalling approach. When we see TCP only traffic, we could assume that the traffic is filtered by some kind of a network firewall. We can detect data exfiltration without decrypting the traffic. So we don't have to compromise the privacy of the user. We don't need to know what is being transmitted to know that this is a file transfer. This is not a movie that's played remotely. However, unfortunately, on the adverse side, the attacker might predict what actions the user is performing. So the attacker will know when the user is sitting in front of their machine. The attacker might guess what the user is doing and possibly what data is being transferred. Is it a file? Is it some kind of streaming? Possibly the visual output could suggest what characters are being typed. So at this point, it is becoming very scary, even though the traffic is encrypted. There are possible mitigations. So the first main possible mitigation is destroying the temporal structure of the network conversation. That would involve inserting some dummy packets into the communication structure. And the second possibility is destroying the spatial structure. And this one would involve padding the packets to manipulate their length. Well, we can only increase their length. We probably couldn't make them any shorter. So there are two possible mitigations. The problem is those mitigations come at the expense of user experience. So if we start inserting those dummy packets, there will be more packets in our network conversation. If we increase their length, those packets will be longer. So they will be heavier, there will be more traffic, it will consume more gigabytes and will require more resources to process it. So unfortunately, if we want this extra level of security to prevent those traffic analysis attacks, that would come at the expense of the user and probably would make the user extremely unhappy because their system wouldn't be so quick to respond anymore. So thank you very much for your attention. I will any question I have.